This project, the genesis of the project, was lessons learned through myself, experiences in the canopy, and my colleagues, my coworkers, other friends out in industry sharing stories. Trial and error is a big part of it. You get out there, you throw I'm going to try something new today, or just a slight variation of what you're working with, and it's just going by feel, right? And making corrections over time that are species specific, environment specific. Policies and procedures where they're in place and where they're complied with. In WorkSafe, this can really steer us into a direction. I think we lack that presence of policy and procedures at the regulatory level specific to climbing, whereas they're quite well defined in traditional forestry and falling. Lastly, personal protective equipment is, the product design phase is looking at rigging rings in the rigging world, but also our climbing methods are producing fewer forces, along with the techniques associated with these new climbing products, for example. Why the focus on falling notches? As I mentioned, the research is in very short supply. I've cited one paper here from Andreas Stetter. That's about it. There's some stuff at the edges, I would say, but focused on arborist practices, there's very little out there. Arborist opinions vary widely. You start a conversation on the internet about, or on social media about falling notches in specific scenarios, you're going to get a whole bunch of flack. And with very little supporting evidence other than like anecdotal, experiential responses. So we're trying to do something a little bit more robust, albeit with a very focused sample, that being hemlock in North Vancouver. And going back to the falling practices, best practices that shape a lot of our falling notches that are in use in BC specifically, they don't transfer across species and scenarios. And similarly, some of the notches that are being trained for arborists elsewhere in the country don't apply to specific scenarios. And that was one of the items that really stuck with me when we started talking about this research project. How does safety improve for industry? The lessons learned are quite important, and this is one thing we can do to change the culture, is like really put those out front and encourage people to share those and talk about ways to break them down and approach the situation different next time. Research is kind of the missing link with a lot of arborist practices, and if there's one thing I can encourage any of you in the group, I went back to school pretty late in my career, but just having that background of experience and training and bringing that into the research world is something you can give back to your community later, so don't rule that out. But from the research, we've got good information to inform product and procedure policy development, then provide the training. Compliance is going to play a role in this as well, whether within a workplace or with a regulator. I'm going to look at a couple of incidents that also inspired and influenced this project. So just a content warning. We're going to talk about a couple of workplace deaths. What's most unsafe about single stem removals? We don't have statistics that provide us with that level of detail and context, unfortunately. But the story sharing gives us some insight. The highest concern is exposure. And with hemlock, often we'll see conditions, you've probably heard a story or experienced this yourself, where you venture into the canopy, encounter something in the canopy, and then you feel like you're forced to make a decision to make a play that isn't ideal. Going back to the earlier results featured in this presentation, the larger the top we're dealing with, we're rapidly increasing the lever on this stem, and with hemlock in particular, that can be catastrophic. So most of the incidents we're seeing right now in the statistics in BC based, falls continue to be a big issue for us, and struck by materials, struck by parts of the tree. This is sort of what we're looking at from the resource, if I go looking in the statistics, these are just single stem incidents that I was able to like kind of flag just through reading. They don't have any coding system. The only reason I got this data is because it was sort of leaked by a friend. This is not information that I could get myself just through the public interface to the statistics, but it gives some indication, and this is, I believe, a 10-year time frame of incidents related to single stems. But again, we see a number of falls. We see struck by materials that are either being rigged or removed, and lots of chainsaw injuries as well. Just a brief review of the stats. The period of analysis here is 2017 to 2021, and just showing struck-bys, about 169 incidents over that 5-year period. And we see 66, a significant number of falls from elevation per year continue to persist. Looking at notch configuration incidents specifically is based on either direct or indirect experience. We don't know how many are out there because it's not coded that way by the people producing the statistics. WorkSafe BC does define falling cut deficiencies as a designated high-risk violation, but does it apply in the canopy? It's a bit of a gray area. We don't have that specificity in the regulations that apply to arborists working aloft. But there has been a big focus in the falling practices side on these deficiencies at the stump. So cutting through your hinge, for example, having a back cut lower than your undercut, poorly cleaned out apex or notches that are too deep, or incorrect notch configurations for specific scenarios. They're very proactive with the falling cut deficiencies, and I would assume that is based on a history of incidents through their investigations where they picked up on that. Speaking to the incidents, just in 2018 and 2022, unfortunately about a year ago this week, we lost a climber in the North Vancouver area in a hemlock that failed while a top was being removed at the base. So some recent relevant cases. The other one was exact same conditions, but in a different part of the province, close to where I live in Victoria, BC, where top was removed as well, and the tree failed with the climber in it. I had a look just briefly at the statistics in the States and in Beaverton, Oregon. We don't know the species, but the tree failed beneath the climber as well in a top removal. What's standard practice? NCZ 133 does not provide notch standards for top or wood length removal aloft. WorkSafe BC occupational health and safety regulations do not provide standards for top or wood length removal aloft. Speaking specifically to notch configuration here, I have seen some scenario-specific standards through like arborist diploma programs, technical schools, that sort of thing, but it doesn't permeate into regulations.
Ryan, quick
Yes.
question.
Yeah.
The fatalities you referenced, were those rigged or free-falling tops?
So the first one in Souk, BC, I'm not sure if they had a rope in the tree in the top. I think that might have been the case, that they were pulling the top end of the tree with a rope, and the stem failed at that point. But whether it failed from the pull of the rope or the force produced when the top came over, I don't know, and it would be very hard for me to get that information. But the second one, no rope, just free-falling top.
Okay, so these were not rigging situations?
No.
Okay, thank you for clarification.
Yeah. What notches are commonly used in the Pacific Northwest? For conifers, primarily Humboldt. Well, let me field a quick dirty study in this class. Okay, here's the scenario. So you're in a hemlock. Let's,
And I perf front.
show of hands. Who's using a Humboldt? Removing a top in a hemlock. You're using a Humboldt. Oh, that's pretty small. Turn it. Show of hands for conventional. A little bit more support. Show of hands for bird's mouth. And Okay, so preference for conventional, that surprises me. For those that don't know, I'm just going to do a quick wrap through what I'm defining as these notches. Starting with the notch angles, open face is wider, but shallow into the depth of the tree. 20 to 25% depth into the tree and about a 70-degree angle. Conventional is typically 45. There are variants. It's acceptable in falling practice in BC to go a little deeper to get your center of gravity working in favor, up to 50%. Humboldt is the same in that capacity. And that's going to be used for conifer top and lengths removal. Bird's mouth is for lifting operations, which hopefully you saw at the field day this week with Bartlett crew. And also for deciduous trees and trees in significant vines as well, where you're trying to avoid a barber chair situation. Humboldt as well, 45 degrees, and acceptable to go to 50% depth to assist in getting your leans into a favorable direction. Over to you, Matt.
All right. Thank you, Ryan. Yeah, so there's the backstory of why we're here. Again, this is early in this project. We did it in February of last year, and there's a massive data set, and we're still crunching data, so this is just the preliminary stuff. It doesn't leave the room. No, it's okay. So sometime in, I don't know, oh, wait, I cut the date off there. Ryan and I back and forth on WhatsApp. What are we doing? So let's examine the force input from a non-rigged piece into the removal. We've got this method of measuring strain in the tree. Let's do it with no rigging. So this is our experimental design. So similar to the last ones, we've got the strain gauges at the bottom. Technology is really cool. Drones have changed from having just cheap accelerometers to having full spatial devices in them with a little gyroscope. So now we can get actual displacement. We're going to stick a little sensor up in the tree and we'll be able to see how it moves around. We're going to put one at the base. And this will be important to know whether or not the tree is stable. So if this moves down here, so this measures strain, elongation, but this shouldn't move. And if it does move, that means the root plate is unstable. So then we have to throw the data out because we put it on the map. So that's why that was there. Particular to this project is we are going to put a known load on it and do a pluck test. So we're going to pull the tree and then let it go back, and that gives us an idea of the mechanics within that specific tree for every time we throw a piece. And where's Nick? There he is. There's Nick on the 5-1, see 5 hits. So he's at the other end on the 5-1, and it's the poor guy, he's like all week long, just all in on that thing. We'd have to do this pluck test after every piece came out. And he's like way down at the bottom of the forest floor. So these are our 3 notches. We kind of standardized them because we needed to standardize them for science. So all the back cuts are the same depth, that sort of thing. This is the site. We're in North Van. This little park here. Ahead of time, we went in and we set anchors in all the trees. We had a fairly limited window. I'm in Montreal, flew out for the project. Ryan and Matt, wherever he is, they spent a couple days just setting anchors so that once we started rolling on the project, we could have a climber in the tree fairly quick. I showed up and went, oh my God, this is not going to work. This is way too steep. This site's incredible. We're so far from the truck, but you have to work with what you got. We managed to come up with a way to run the computer in the forest for a while, extra batteries, and a lot of humping up and down this fairly steep slope. So the pluck test is kind of cool. Normally, it's just how you make things work. Normally, you have a release shackle or something like that, and it's on the ground, but the rope was so long we couldn't do that. So Ryan is in the tree, and Ryan, don't move, because if you move, you're going to change the dynamics of the tree. So you have to be a static mass damper up there all the time.
Okay, going in 3, 2, 1.
So Nick managed to get about 230 kilograms of lateral force on a tree on that, and then this is the resultant response as we go back and forth this way. So then we would do that, and we'd throw tops, and we'd throw more tops, and we'd throw more tops, and we'd throw more tops. And in total, we threw 27 tops. And then we weighed not everything. It was just too much to weigh everything, but I weighed kind of a sample of stuff to give us an idea of what the mass of the wood was. We knew it was relatively dry. Didn't want to go to a green wood chart. So this kind of gave some idea. Just hoisted stuff in the forest with a 5-to-1 and Nick. Okay. Oh. So this is kind of our resultant data. This is not the data coming out of the computers, but we go through, we did all kinds of allometry. We have things like how high the cable was in the tree, the notch height, the length, the number of pieces in the piece, back cut depth, notch width, calculated volume, tons of stuff. So that we can kind of make a model. And so Ryan did really well. I think I have some outliers here. These are my guys. But we really consistently had the same sort of size of cut. So the ratio of the back cut to the diameter was nailed by Ryan, and not by me. And so our basal, all of our trees, we had no motion in the bottom of the tree. So this is the piece coming out, spatial sensor up top, and we see nothing down below. So we know that the root plate on the tree is still. The last one, we talked about just straining in one direction, and the reason we do that is, so we've got both straining gauges. There's one, this is in the direction of the falling top. This is the one that's perpendicular, so it's measuring strain this way. It's really hard to interpret this data because it's not over time. So this is the actual motion that the stem is making. So it's not just straight back and forth, it's doing something like this. So the tree spent most of its time here. And then it has this one big sway out, and then this other big sway back, and then it starts to do this. But this is kind of hard to interpret, so we rely once again on one data point. So we took, we get more results like this. Super cool. So we know here that this piece, this was a top, and it hit the tree on the way down here because there's this little funny blip in the data. This one didn't have nearly as much dampening because there was no limbs below it. So back. Oh yeah. The important part is here we've got two things. So this is the first bending moment. Branches going back. So down is back and up is forward. So you notice the first big thing that happens is this backwards movement. That's the push back. So you know when the piece starts to go over and you go backwards, that's this motion. And that's going to be one of our key data points. We'll skip that, just some more trees, samples. Okay, so if we take the length of piece, we had, this is like early data exploration. I'm like, okay, this is the low, the initial pushback by the length of piece. I'm like, there's nothing here. Our job is, if this line had some relationship between the two, then we knew we had done a good job of science. And there's nothing here. I'm like, I lost my mind. I was like, Ryan, we got to do it again. And I realized, wait a second. All these points over here, these are the original tops, way up at the top. And this is by length. They're really long, but they're really thin and light, and they were dry. So I take them out. We look at just logs, and whoo, a line shows up, some sort of relationship. And then I'm like, oh, wait a second, let's take out all the other notches. So we've got different notches in here, and things get even better. So this is the relationship to the initial pushback and the length of log. And we see that as the piece gets longer, we get more pushback. That's good for making a model. This is the forward pull, same thing, and very similar relationship. So, we've been here for 50 minutes, it all comes down to this slide. Okay, so this is pushback. This is our bird's mouth, Humboldt, open. there's not really a big difference. And our hypothesis was at the beginning of this, we're like, okay, if you use a more open face notch, then the piece is going to fall longer and the hinge is going to stay there for a longer period of time. The piece will have gained more momentum, more energy will be in the stem, and on the pushback, that probably won't make a big difference, but as the notch starts to close and the piece falls over, you will potentially pull the piece further in the direction of falling. So that was kind of the hypothesis. We're supposed to say that. So we pretty much nailed it. So there's a little bit of difference here, but this is statistically the same. But this is cool. So this is our bird's mouth with 50, so oh yeah, there's all kinds of stuff to do to figure out how much force that is actually happening. With almost twice the amount of forward pull in the stem compared to the humble, and maybe 75% more. Statistical significant difference between here and here and here and here.
One on the right is an open.
Yeah, this is open face, okay, so 70 degrees. This is 45, and then our bird's mouth is 90 degrees. That was almost it, but then I was like, for this presentation, we have to have some take home. I was like, wait a second, we've now built a model that we can model length. Yeah,
So what was it, the conventional face and the Humboldt would have the same forces?
they're pretty close. Yeah, statistically, more money, more time, more tops, and we'll probably clean this up, and we'll see better relations. We have 27 samples. We have about 6 or 7 of each. Some of the stuff had to get tossed because of problems. So we can build this data set up. We'll see better relationship just because of how. But yeah, we're not seeing a big difference between those two. We see this huge difference with the Prisma.
Was the conventional on there?
No. It was a modified open face. So it was a 70-degree. 25%.
Yeah, so it was just like...
Yeah, exactly. Okay, so now we have this data and an understanding of how much force the piece is putting in. We know that our tops, we're putting, our 5-meter tops, we're putting about 25 kilograms, 55 pounds, of backwards force into the stem. And 50 kilograms of forward force. That relates down at the bottom to about 1,500 Newton meters of rotational torque. So we got all this from those podcasts, like understanding how the tree moves. That's 1,100 foot-pounds of torque. That's a lot of ooga-oogas on the impact gun, right? If I go down 10 meters and throw the top out of the tree, kind of somewhere, not quite to halfway, but up there, it's only 80 kilograms of back force. It's not that much more. But man, it's 285 kilograms of forward force. And that's an increase of 4,200 foot-pounds, 5,700 Newton meters of force at the base of the tree. Because lever length is important, but you're still high in the tree. You're putting a big bending moment on. And so this is that, okay, do not take big tops halfway up the tree because of what it's doing to the base of the tree. No way. So last night, jumping around, we have something on the project. So finally we have some, and we're gonna keep building on it and like refining it. And I had a conclusion slide, but I somehow deleted it. It doesn't work out here. So anyways, the conclusions out of this are preliminarily, a more open face does provide this opportunity for the piece to fall and capture the stem and pull it with it. What does that mean in practice? Well, it means certainly probably a narrow notch, get the piece going, get it in this direction, and then get rid of it. Does that mean blowing the hinge out? It might in your case. Does it mean making step cuts or something like that? We're still working on it, but that's where we're going with this. And then, don't throw it in the box.
So just a question. Did you do testing with kind of like conventional, basically similar
okay, we back and forth, we knew how many trees, and the number of days we had. And we actually originally were just gonna do 2 notches. And then we decided, okay, we think we have enough time to throw in this third one. Yeah, it would be great to look at the differences between just a Humboldt 45 and a 45 degree. I think we're not gonna see much difference there. But this is the strain information at the base, which is a damped response. I still have to look at the spatial information from that spatial, and that's much more complex. I think we will see some differences at a faster time resolution. So things will happen faster up there. This is a well damped at the base, and this is what we're interested in, is what's happening at the base of the tree.
Because, like, obviously, the theory is that on a Humboldt, the tree will slightly slide off. Rather than completely just like.
Push back, yeah, exactly.
So is that, do you think that's why it's a little bit lower than the middle?
That's what I think.
I was just gonna point out that all of these samples are branches on the stem, so you could expect like greater forces if this was off.
Because of what we showed in the previous project.
Yeah. Clarifying what you said a few moments ago, between the difference between the pushback and the forward force.
Yeah.
That with the bird's mouth, the open face notch, I think what I heard you say was that the hinge fibers still intact are pulling the stem forward before the face has closed and broken the hinge.
Which is correct.
See, I was supposed to have more labor here. This is a bird's eye. So we've got some pushback, but then we have this massive spike going forward, and I think that's what's happening. So yeah, the fibers are still holding. The piece has been falling. It's gained a lot of its potential energy, is now kinetic, and it's ripping at a pretty good rate of speed, and it's still attached. The tree's been pushed back, and now it's starting to move forward in the other direction, and the piece is still attached. You might as well be breaking almost, right? Because it's still, and then boom, and then we get this really fast response when that happens. So again, we still have more to plug away, but we think that's what's happening. Yeah.
Thank you.
I was gonna say, so on live trees, that would be even more accelerated, except you wouldn't necessarily be introducing the risk of failure at the base. With live trees, you're certainly gonna get a lot more flexibility and more activity in one of the top right. Live trees as well.
For sure, I think so. You know, it depends a little bit. Long fibered coniferous trees, even when they're dead, they have, you know, that ability. You can lay them over and have them still hanging on. Big leaf maple, you know, it's fibers are gonna break halfway over, you know. So but I should. Can we go over a few minutes? And we can talk out in the hall too. Bring it back there fast enough. In this project, we have the original data from when the piece, is it here? When we threw the first piece on that project, the rings one, it had a full hinge. And the cool thing was, and it weighed a lot more. So this is the caveat. If you're rigging, everything changes, okay? This is specific. When we left the hinge in, we got a lower force with more mass. And I think that's because in the rigging scenario, the energy is being put into the rigging. That's what we were worried about. That's where the big problem is. As the piece went over, it was killing potential or kinetic energy, breaking the fibers. And so even though the piece weighed 100 kilograms more, because it was a rigging scenario and we were worried about capturing it in the rigging, it had less energy when it hit the rigging because we were breaking fibers. So if you're rigging, you want a big notch and you want it to, you know, sort of break over and spend a lot of time crushing fibers because that piece goes slow and